And I'm here today to talk about type traits. Now, there's been a lot of talk here at the conference about template metaprogramming and SFINAE and throwing a bunch of things around. And this is meant to be a gentle introduction to those kind of things. If you're the kind of person who spends all your days writing templated code or maintaining a standard library, this is probably going to be a little slow for you. But if you're wondering what all these things are and why do you care and so on, then that's what I'm here to tell you about. Okay? Like I said, I work at Qualcomm. I have an occasional blog that I post on it whenever something, inspiration strikes. I seem to be averaging about 1 or 2 posts a year. So if you're interested, there you go. So let's start off right away. So what are type traits? There's a whole bunch of words. Type traits are compile time, template, meta functions that return information about types. That doesn't really help. So let's move on. Let's just move on to the next one. So what? Why do I care? What do they do? Why do I care? And the answer is maybe you don't. If you are writing code that is, shall we say, about concrete types, about your concrete code, you're not writing templates, you're not writing algorithms that work on different types of data types, if you're not working on things that you're not writing a container that can hold any kind of types, you probably don't care about type traits, and that's fine. But on the other hand, if you're writing code that is designed to work on different kinds of types at different times, sometimes you need to know about that. How many people here have seen some of Sean Parent's talks besides the one he did this morning? There we go. One of the things that he likes to talk about is he has given talks about algorithms, writing algorithms. And basically one of his goals is no naked loops. He said basically anytime you write a loop in your code, you should think about this. And he said, is this something that I'm going to do more than once or more than twice? And if so, you should factor it out into an algorithm, which is usually a templated function, and give it a name because, well, things are much easier to reason about when you can look at it and say, oh yeah, I know what that's doing. That's doing a rotate, rather than looking at a loop that's shuffling things around and trying to figure out, this kind of looks like a rotate, but maybe it's something else. Maybe it's, an interleaving things or something like that. But if you see the word rotate, unless one of your coworkers is being really evil and trying to mess with your head, you say, oh, I know what that does, and you move on. So that's one of the cases where people are writing a lot of generic code these days. Anyway, but the point is that if you're writing code that has to deal with different kinds of types, if you're writing a template that might be instantiated on different types, sometimes you need to know something about a type. And that's where type traits come in. Okay, so quiz, little quiz. How many different kinds of types are there in C++? There's effectively no end to the kinds of the number of types, right? And I'm not even saying how many types are defined in the standard. There are hundreds, right? But there are a taxonomy of types in C++, and in particular, there are different classes of types. For example, excuse me if I'll use the word class. There are classes. There are references. There are 2 kinds of references, L-value references, R-value references. There are pointers, and so on. Anyway, so there's a reasonably small and well-defined number of kinds of types. Now, some of these types contains all different kinds of concrete types, even if that sounds really odd, doesn't it? Concrete types. There are some of these classes of types have a few specific members, and we'll see that. And some of them are open-ended, like class, because you can define your own. But in any case, it turns out there are 14, just so you know. And there they are. Interestingly enough, you can have fun in trivia contests if you want and try to name them. Void and null putter are, in fact, the two that everybody has trouble with. Null putter because it's probably the newest one, and void because that's the class nobody thinks about, or the type nobody thinks about. Right? You can't have any variables of type void, so why would you think that you would have why would it be one of the types? But it is. It's one of the 14 kinds of types you could have. So null putter, void, only have one element, one member of those sets of classes. Array and pointer and class are open-ended, and union and enum and function. Floating point has 3 members. Yes, question here?
What about structure?
Class. Yes, struct and class are the question is, what about structures? Structures and classes in C++ are really the same. The only difference is what is the default access. By default, everything in a struct is public unless you say otherwise, and by default, a class, everything is private. Another question, yes? What's the difference between array and pointer? A pointer doesn't actually have any storage. It points to something allocated somewhere else. And an array is actually, well, it's an array. It's a storage, it lays out storage, a contiguous collection of elements. And in fact, decay, when you pass an array by a value, it decays to a pointer. Or if you use the type trait decay, you can tell how things decay, how things get converted. But yeah, a pointer is just a pointer. There's no actual elements there. A pointer can be null. An array can't be null. You can have an array of 0 elements, but it's still an array. Any other questions? Okay. This is a really handy slide that Howard Hinnant made up several years ago and is kept up to date. And it talks about the different kinds of types, those 14 kinds of types, and some of a few other things that you can see in that we'll talk about along the way. You see that, for example, this big circle up at the top, those are the integral types. And there's actually a few more now since this has been made. If you Google up, this is available on GitHub in Howard's repo, github.com Howard Hinnant. Kind of look around in there, or just Google up, Hinnant type chart. It's actually quite handy. But if you look, for example, look at, fundamental types, arithmetic types, integral types, you see there's a whole bunch there: int, long int, unsigned int, and so on. And now there's uint 8t and int 8t and so on. Fundamental types: void, null putter, floating point types. And when you think about types, you realize that there really aren't that many kinds of types. I mean, obviously, classes, there's an infinite number of those. Anyway, so how does this get back to type traits? Okay. Basically, what a type trait is a structure, a templated structure that when you specialize on a particular type, it has members and or nested type defs that tell you information about the type. Sometimes, sometimes the result of a type trait is another type. Sometimes it's a value. And we'll talk about both of those. We'll give an example here. Whoops. Come on. There we go. Okay, real simple type trait. Is floating point. Basically, is floating point. You specialize it on a type, some type, can be any type at all. And it has and this expression, said floating point of whatever type value, is true for the 3 floating point types. If we go back to Howard's chart here, you'll see up here under floating point, there are precisely 3 members there. There's float, double, and long double. And it's true for all of those, and false otherwise. This is not working as well as it could. So, anyway, next one. The result of a type trait does not have to be just an integer. or a Boolean, I should say. Just doesn't have to be a Boolean. Here we have rank. Rank is for working with arrays. It will tell you what the rank or the dimensionality of an array type is. So for example, if you say rank of int, : value, it gives you a value of 0 because it has no dimensions. An int has no dimensions, it's just a single variable. Int 5, for example, is an array of 5 ints. The rank of that is 1 because it's a one-dimensional array. And so on for 2, 3, 4, whatever. Okay, the way this works is that the whole value thing is that these templated structs have constant non-member basically static member variables. They have static member variables associated with the struct when they instantiate it, and it holds the value. The nice thing about them being constant is that you can deal with them in C++ 11 and later. You can deal with them at compile time, and the compiler can use these to control the instantiations. But a lot of the type traits we use a lot are the ones that are just basically Boolean things. Is this a floating point type, or maybe does a type have a particular property? Is this type default constructible? Is this type assignable from this type? And so on. But we can also do things like generate new types. One of the ones that we use a lot in the standard library is remove const, or actually another one of these, which is remove CV, which removes both constant and volatile. And this is what it does, is it takes a type and it gives you another type. Remove const of const int, : type, is defined to be int. Remove const of int is also int, because there's no const to remove. And so type is going to be a nested type def inside the struct. So if you were to look at this, you'd see struct remove const. And basically in C++ 14 and beyond, there's shorthands for these. You can say remove const underscore t for constant, which gets rid of, which means it's a shorthand, it's an alias for : type, and remove rank : underscore v for the value. And this saves a lot of typing if you get really complicated in there, because otherwise you look at your stuff and it seems like every 20 characters you have to type : type or : value, and it makes it hard to understand what you're doing. But it doesn't change what you're doing, it's just a little syntactic sugar. Okay. There's no reason that a type trait has to return just one result. Structures can have any number of static member variables. They can have any number of nested type defs. There's no reason that you're limited to one. I bet I can think of one off the top of my head that returns, 5? Iterator traits. How many people have used iterator traits or know what they are? Yeah, there we go. Iterator traits has 5 nested type defs. Pointer, reference, iterator category, value type, and what's the other one? Difference type, that's what it is, difference type. But so it tells you if you're a random access iterator, forward iterator, and so on. And it tells you, for example, value type will tell you if you dereference this iterator, what's the type of the thing you're getting back. And this is really handy when you're writing algorithms. For example, if you were going to write something like, say, sum, okay? Write something that takes a pair of iterators, begin and end, and it's going to return the sum. So conceptually, this is really simple, right? You start with 0. You add the first one in, you add the second one in, you add the third one in until you're done, and then you return it. Really simple. But you start with 0 of what? And the answer is you start with the 0 of the value type of the iterator. Anyway, I'm getting a little ahead of myself because the next slide is, yeah, this is fun, but why would I do this? And so, yeah, I just skipped 3 slides ahead. Why would I use them? Well, because when you are doing generic code, sometimes it's really handy to do that. And yeah, writing algorithms. I talked about sum, where you need to know what type to return, and also what type to, what 0 to start with. If you wanted to do a factorial, you need what type to start with 1, right? You start with 1 and you multiply. Same kind of thing. But the other thing is that iterator classifications, iterator traits are really, really handy when you're writing some kind of complicated algorithm that has to do with traversal, because the different kinds of iterators can give you different kinds of, different categories or capabilities. A real simple example is permutation. Permutation is a very useful call that says, is this sequence a permutation of this sequence? They have the same elements, but in a different order. And this is an expensive operation to do. I mean, it's an n-squared operation, which can be very expensive if you have large sequences. But sometimes you need to know that. And if you have random access iterators, there's a quick out in some cases. The first thing you do is you can look and say, how long are these sequences? And if they're different length, well, you're done. You know that one's not a permutation of the other, because the shorter one it's not going to have the same elements as the longer one, because there's at least one missing. Sorry, I'm going to try to not walk around so much. But in any case, and we use that in permutation, mismatch, equal, and a bunch of other ones. But because forward iterators or bidirectional iterators, calculating the length is a linear operation, which in a long sequence can be expensive. We don't do that for those. And so it's an example of the kind of things where iterator traits is handy. I talked about the returning a value from a sequence of passed by iterators. You want to know what you want to return. What type do you want to return it to? And the other thing is it gives you information about the objects that you're dealing with. It can tell you what kind of operations you can or might not be able to deal with. I forgot remote. Excuse me, I'm having a hard time talking today, and I'm not sure why. Rotate. Sean mentioned rotate this morning. Rotate is, at least current implementations of rotate are actually quite a bit easier if you have random access iterators rather than you have just forward or bidirectional iterators. But now he suggested that today that he has a way of doing it with forward iterators that's just as simple, which means I have to have some reading to do and some experimenting to do, which is fine. So, any questions about algorithms? Thought I saw a hand. Nope. Okay. Another use for type traits. Restricting templates using enable if. So this is going to go, we're going to have to do a little background with this. If you're writing let's say a template function, and you want it to work with only a certain set of objects. There's a facility in the standard library called enable if, and it has to do with using the second ugliest acronym in C++ called SFINAE. The first the ugliest one for me at least is RAII, because I can't actually say that without spelling it out. But they're both kind of silly. So basically, this is enable if is a packaged up version of a SFINAE technique to restrict the compiler from using your templates for certain kinds of types. And I'm going to run through an example, and we're going to talk about how this works. So it comes down to when the compiler is looking to call a function or make a template, make a type or something, it builds what is called a candidate set. It builds a set of all the possible overloads that it might that match the call. And then it goes through and ranks them and picks the best one. Okay? In this case, I have 3 different functions named unimaginatively func. Yeah, I know. I have no imagination. The first one, it's a C-style varargs function. Right? It takes anything. That's not a C++11 variable argument pack list at all, and it returns 0. And the third one down at the bottom takes a float and returns 2. And the one in the center is a template, and is decorated with a whole bunch of stuff. Standard enable if blah 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 blah. So let's pretend for a minute that enable if is not there. Okay, and if we didn't have the enable if and we just ran this code, does anybody have any idea what we would get? You'd get 1 every time. That is not quite right, but certainly we'd start that way. We would get that way. In particular, yeah. Right. The third line there is an exact match for the third call. And the compiler will always prefer an exact match of a non-templated function over a templated function that takes everything. But yeah, the first call would print 1. The second call would print 1. The third call would print 2. And kind of surprisingly, it's a double, but it's also implicitly convertible to float. Yeah. Anyway, so, but you say, no, I really want it just to be integral. And so, with the enable if there, what happens is that if the condition in the enable if, the standard is integral t : value, is not satisfied, this actually generates a compile error inside the template and causes the compiler to drop the template from the overload set that it's building, which is where the ugly acronym comes from. It stands for substitution failure is not an error. So when it substitutes float in there, the template fails to instantiate because of a syntax error, and the compiler just drops it out. So SFINAE, so substitution failure is not an error. Anyway, and so what happens is the first line, null putter. It's not integral. It's not float. It falls back to the C-style varargs, which the compiler uses. The compiler considers C-style varargs to be pretty much the lowest form of matching. It will try pretty much everything else first. Anyway, or it will. Let me rephrase that. It will prefer just about everything else to that. So, but null pointer is not float. It's certainly not integral. So it will print a 1. Yes.
Did I miss it? What is that second parameter on?
Okay, the second template parameter on there is in fact the return type of func. And basically what happens is, what enable if does, it takes 2 parameters, it takes a condition and a type, and it either causes the substitution failure, or it defines inside of itself : type, which is the same as the second parameter. And so it is set up to use, in the preamble of a function for the return type. In the defining the return type. So yeah, you end up with, you just say standard enable if condition return type : type. And it's always the same as the return type, or it fails to instantiate. Anyway, So yeah, the second call says, is integral? Yes. And it will pick the second function because that's a better match than float, and it's a better match than the ellipses. Okay, the third call, 2.0f. Now that is not an integral type. And besides, it's an exact match for the third call, so it will print 2. And the fourth call, interesting enough, will also print 2. It cannot actually satisfy the second call, the templated version, because it's not integral. But there is an implicit conversion from double to float. And the compiler will prefer to do an implicit conversion rather than to choose the C-style var args.
Don't you get a narrowing warning though?
Depends. Depends on your compiler. Depends on how good your compiler is. The question was, once you get a narrowing warning from your compiler, and it depends on how good your compiler. A really bad compiler, no narrowing warning. Okay? A better compiler, you'll get a narrowing warning. A good compiler will say there's no loss of value doing a floating point, a double 2 to a float 2, no warning. So if you have a bad compiler or a really good compiler, you'll get no warning. And if you have something in the middle, then you'll get a warning. Warnings are kind of funny. It's like, we like compilers to put in warnings because they catch things, but as the compilers get better and better, that would be a false positive on the warning. You'd say, yeah, I'm converting a double to a float. Maybe there's a loss in precision there, but it's a constant value and there's no loss of precision there. So a warning would be a false positive there. Yes?
Sorry, quick question. Back before when you said without the enable if guard, would it prefer to do the implicit conversion or use the template?
Without the, so the question is, without the enable if guard, will it pick the template or do the conversion? And I believe that he is correct that it will choose the template because it doesn't have to do a conversion. If you're going to do this, it's really good to spend a little while experimenting and find an article about matching of overload sets, so you can be sure of what's going to happen. Because basically, what you're doing is you're saying, as you set these up, you're saying, I want this to happen in this condition, and this can happen in this condition, and this can happen in this condition. And you want to make sure that those actually do happen, that the things you want to have happen, happen. Hand here, thank you.
Sorry, so the first call you said print 1, but meant 0.
Yes, I'm sorry, I meant 0. This prints 0, 1, 2, 2. Yes?
I'm just going to ask, in terms of the enable if version, could you have multiple overloaded functions with enable if, or is the compiler going to basically say that you're running a version of that and you can't do it again?
Okay, so the question is, if you set this up so that you do this, have enable if here, can you have multiple functions each with enable if on them, and will the compiler complain about that? No, the compiler won't complain about that. The most common thing I see actually is 2 of them. One that says enable if something, and the other one says enable if not something. But if you you should be able to have as many as you want, as long as you're not ambiguous. The compiler has strict rules about which is better, but all the templates are going to be pretty much the same. And so if you had 2 that matched something, the compiler would say, this is ambiguous, I don't know what to do.
So yeah, for instance, if you instead of the in function float version, you would say, enable if is floating point value, floating point 1 in that case.
So the comment was, if I had another one there where the enable if statement said is floating point, would it pick the floating point calls here? And it would certainly pick the 4th one, the bottom one, but not the third one. And the reason the third one, it wouldn't pick the third one is because there's a better match. There's the final function down there that is non-templated and takes a float. The compiler will choose that. Again, I mean, the language has a set of rules for matching out of candidate sets. And if you're going to do this kind of stuff, you really want to look at those rules and be very clear on them. But one of the rules is if it has a direct match that's not a template, it will take an exact match for the over the template. Question here.
It's my ignorance. Is it possible compiler allows you to do Boolean operations on the is integral or, say, for example, is floating point in that statement there?
So the question was, are you allowed to do arithmetic operations on the conditions there and say, is integral something or is floating point totally valid? Yes, you are. And in fact, in the standard library, we have various ones of those. Like is not a reference and is not something else, say, or is not a reference or is a pointer. Anyway.
I believe basically it's anything that's a constant expression.
Right. Yeah. The comment is that anything that is a constant expression, that's true, and it has to be known at compile time.
Anything that can be evaluated by the compiler to a constant expression.
Okay. Other questions? Okay, we're going to leave the SFINAE example and go on to a different example of why you want type traits. You can, if you're writing generic code, sometimes it's worth your while to not be generic. Okay, you can provide optimized versions of your generic code for some types or types that hold particular properties. And I'm going to use the classic example from the standard library, which is vector pushback. Okay, I'm doing this because it's an interesting example and because everybody wants to write vector at some point, right? How many people have tried to write something like vector? Yeah, sure. I mean, it's like everybody knows they can do better than the standard library, and then they try it and they discover it's really complicated. There's lots of little corner cases. Anyway, vector pushback. Vector pushback has a strong exception guarantee. That's written in the standard. It basically says that pushing back something either completely succeeds or it throws an exception and the vector is left exactly, is left in the same state as it was before. It has the same capacity, it has the same size, it has the same objects. Okay? A vector has both capacity and size. Actually, it may not actually guarantee that it has the same capacity, but that's the way it's always implemented. Vector has capacity and size. A vector allocates some space and then fills it along the way. So there may be unused bytes at the end of the vector waiting for you to put more objects in. Okay. Most of the time, when you push back, it's really straightforward, right? The vector looks and says, yeah, I got space on the end for another object, and it copies it in, and we're done. That's fine. Okay, that's not the case we're going to talk about, because that's the easy case. The more general case is when the size is not, there isn't room at the end of the vector for the object you want to add. And this applies to insert and all those other calls where you might be adding more than one, but pushback is simple as a one. Okay, you allocate a bunch of new memory, some amount bigger, right? You copy the objects one by one over into the new memory. If any of those copies fails for some reason, it throws, you say fine, and you destroy the objects you copied, and deallocate the memory and rethrow the exception. The original vector is unchanged, right? You haven't done anything with the original vector. And this is the way things worked in C++03. This is a very good way of dealing with it. It satisfies the strong exception guarantee. It's fine. Everybody good with this so far? So, what if, but C++11, Howard's not in here, is he? We have move semantics now. Moving is supposed to be an optimization of copying, right? Moving is supposed to be faster than copying. And you think, we can do better than this. We can get better performance by using move semantics. Okay, so fine. But there's a catch. Remember the strong exception guarantee? Let's just talk about a naive way of doing it, right? We allocate some more memory, a bigger memory, and we move things over from one to the other, to the other, to the other, to the other, to the other. But what if one of the moves fails, right? We say, we've moved 5, and the 6th one failed. Okay, well, let's move these 5 back. What if one of those fails? We're stuck, right? We are just stuck. We cannot satisfy the strong exception guarantee anymore because we've done a destructive operation and we can't get back. Okay, but we want to be able to move things. Things that are expensive to copy, we want to be able to move things. If you have like a vector of maps, right? Copying a map is expensive. You have to reallocate all the nodes in the map and everything that's in those pairs and so on. And you really want that to be fast. And so what vector does is it does this operation, but only if the type that's in the vector is no-throw move constructible. If the type can guarantee that moving it will not throw, then you can do this operation safely because you move, and then destroy, and update the pointers. Then you're good to go, and you get the speed up and the exception safety. But you have to be able to move construct something without having it throw ever. Important safety tip: if you are writing a type and you expect to put it in a vector, or actually just in general, you really want your move construction and your move assignment operators to be no throw or to be no except, if at all possible. Okay, sometimes it's not possible, but in general, you want them to be no throw move except, or no throw move assignment and move construction. And this is only one reason. Okay, everybody good with that? But we can do better sometimes. What if you have a vector of ints? Okay, what if you have a vector of ints? What if you have a vector of structs that contain an int, a float, and a char? Okay, what you really want to be able to do, what people come to me all the time is like, what I really want to be able to do is I just want to be able to allocate some memory and memcopy them from one to the other. Just pick up the bytes and lay them down and I don't care what the structure is, just put them down there. There's a type trait for that. It's called trivially copyable. So if in fact your type is trivially copyable, and there's a list of things it has to have, basically if it's a struct, it has to have all the members be trivially copyable, and I think it has to have a trivial destructor as well. But basically, or as a trivial constructor, excuse me. And basically, if that happens, what you want to do, if you're in your implementation of vector, is allocate a bunch of memory, memcopy from the old memory to the new memory, and then destroy the old objects and update your pointers. No worries about exceptions, right? Memcopy never throws. And no worries about your destructors throwing, because destructors can't throw. So this is almost certainly faster than anything else. Although if you're writing a vector replacement, you should have tests that measure this and make sure that it really is faster, that it's worth doing, because it is adding extra complexity. But this is an example of where a type trait can really be a win for you, both the move semantics and the trivially copyable stuff. Yeah, as I said, these are optimizations. Okay, You can make your users happy with these optimizations, but none of them are necessary for correctness. Your program, your vector will be correct if it does things, copying the objects one at a time and then destroying the old ones. That is not an incorrect implementation. This is just a faster implementation in some cases. Okay, and you do this by comparing. When time comes for pushback, you can say, is trivially copyable t : value? If that's true, call one routine. If no throw move constructible, call another routine. Else, do the third one. You can do that. You can use some kind of templated tag dispatch, or you just have a branch set of ifs. Anyway, this is the kind of thing that a lot of containers do. They help you right out. So this, okay, we're good for time, right? 15 minutes. This is the kind of things that people do with type traits. This is the first kind of level of type traits, doing comparing and testing. If you want more information, these are two very nice books about type traits. They're both about 8 or 9 years old. This one is called Modern C++ Design by Andrei Alexandrescu. Andrei is here at the conference, and he is giving a talk. I believe it's tomorrow. It might be Friday, but I think it's tomorrow. And I borrowed these books from the university bookstore out front, where they're selling them. This one is actually signed by Andrei, but I'll be returning it. So if somebody wants to buy a signed book, well, there you go. But this is this book was written 10 years ago, and it does not talk about move semantics or a bunch of other C++ 11 things or 14, but it talks a lot about template metaprogramming, and it builds up a framework for doing template metaprogramming. There are lots of frameworks. This one was called Loki. This was one of the first. But you can learn an awful lot of principles on this. Both of these books, this one is by Dave Abrams and Aleski. This is a little later, and there are more examples. This one's based off the Boost type traits library and the Boost metaprogramming library. Both of these books go quite a bit farther than I have in this talk. They build up very, very intricate and complicated frameworks for doing intricate and complicated things. But when if what I've done here today has given you an appetite to learn more, these are good places to go. Okay. Oops, sorry, I thought I was on that one. Okay, other questions? Yes, in the back.
So, can you show the slide again? You said it had the 0, 1, 2.
Sure. 0, 1, 2, 2. Yes.
Is that where it says is integral and then int? Should that be t? Oh wait, no, I'm sorry.
Okay. For the video, the questioner withdrew his question. Yes.
One of the questions, because a lot of type traits you said are in the standard library, is it possible when you're, say, generating some generic new class or just generating a new class in general, and you want to check to see if a copy of that class is filled at compile time, could you also generate your own type trait for whatever purpose?
The question is basically, can you generate your own type traits? Absolutely. There are a few type traits in the standard library which are really hard to implement in the language, okay? And basically, we depend on compiler support for them. But in general, most of the type traits are just written. I mean, you can imagine how to, let's look at is floating point, okay? Whoops, too far. Is floating point, all right? Think about how you would implement this. You have a primary template that that has a static member variable set to false. And then you have 3 specializations, one for float, one for double, one for long double, that set the static member variable to true. Done. Okay? There's nothing preventing you from writing your own type traits. Sometimes you have to go to more work than that to figure out how to do them, but frequently it's very simple. Walter Brown gave a talk last year here about using void T to do basically detection of capabilities on types, and you can certainly use that to create your own type traits. You can say, does a particular type have a member function named foo that takes an int and a float and return a stud string? You can write your own type traits like that. Okay, in the green and then in the brown.
So, working with an older code base, say it has old like C-style cast and void pointer pass through, what does that do to the system if those end up being tried? It counters one of the variables that's mounted at the casting or.
Well, okay. The question was if you have an old code base which has a lot of passes around void pointers and has a bunch of C-style casts and so on, what happens there? Well, the thing is, once you convert something to a void pointer, you've lost all the type information, and so any of you try to do any type trait stuff, all they're going to see is void star, and so you're going to end up with working with. Well, if you do a C-style cast, okay, the type is now going to be the result of the cast. No, it doesn't do any checks. It doesn't look past the cast. Yes.
So for the SFINAE check, is there any benefit to having it as the return type versus part of the template signature?
Okay, so the question was for the SFINAE thing, is there a benefit to having it as part of the? I went too far. Basically, there are 2 ways to do this, okay? There's one with enable if and incorporate it into the return type. And the other way is you can define a second parameter to this that is a pointer to some type that is only around for integral types, basically, and then default it to 0. And so when you call it, the 0 gets filled in or the substitution failure happens. And the question is there any benefit to doing it this way as opposed to that way? In general, this way is considered cleaner. The other way is necessary for some things like constructors which don't have a return type. But if you add a default parameter to a function, somebody can pass a value to that. Okay, and you probably don't want that. And it's one of those things that you just if you do it this way, you do not give your users an opportunity to misuse it, whether due to error or malice, either one. And so it would be terrible to see somewhere in your code a call to func 2, 4, and you wait, what just happened there?
But listen, in this case, can't you just put it as part of the template signature on the top? It's not part of the function signature.
The question is, can you put it as part of the template signature, the template parameter list instead of the function signature? And in many cases you can, but then again, somebody could say func bracket type list. It's not an awful way to do things. It's just this way is, it leaves off classes of errors that are rare, but still, I'd rather not have to actually explain to people that.
The only reason I'm asking is if you look at the return type for this function, it's not exactly trivial just by looking at it.
It's not.
You have to look at the right place.
Yes, I agree. The return type, figuring out the return type for the second function up there is not exactly trivial. As the gentleman in the back who was asking me a question about it and then said, oh, no, I see it. I agree. Better indentation would help here, actually. I tend to, this is kind of more slideware than anything else, but I tend to, when I'm writing these, I tend to break after the comma, after is integral value. So the line below func is, int : type. And so I know where to look. But that's a convention I use rather than a universal kind of thing. Who is up first? I see a hand here, hand there. Anybody know? You go ahead. You'll be next.
Just wanted to comment on that one. Maybe in the future we would be using concepts, and then this would just go away and resolve itself.
Yeah, concepts are going to change the way this is done a lot, because what you'll do is you'll write a concept that says requires something to be an int. Yes, over here.
I was just going to ask, instead of putting the type name there, could you do it the C++ syntax 11, 14, or 11, where you do auto, and then you could actually do a type declaration on the right?
So the question is, can you use the arrow syntax and put the return type somewhere else? I've never considered that for enable if, because then you still have to have the enable if phrase somewhere in there, and this lets it fit right into a function declaration where you have template, return type, function name, parameter list. You had a question behind him, yes.
So can you help me with my mental model of SFINAE a little bit? I'm trying to understand what happens when say, func of 2, that's going to print 1, right? Func of 2 is going to print 1.
Yes.
Okay, so, but think about func of 2.f. Like we know first of all that that's going to call float of f, whether or not the enable if check is there, as we said, right? Because it refers to one that's more specific. But suppose that I want to understand what happens when enable if fails. Like what I imagine happens, but I don't think that this is actually what the compiler sees at all, is that those 2 lines just disappear and there's sort of no return type, and so it looks like malformed code, and as a result, like the compiler says, okay, that's not what's going to happen. But I don't think is that actually the way it works? Like, is that mental model accurate?
Yeah, well, I don't know about the two lines disappearing, but the rest of it is very accurate. So to rephrase, rather than rephrasing your question, I'm going to try. Rather than answering your question, I'm going to rephrase what you said and then agree with you. That what happens is, for the fourth call here, 2.0 double, it attempts to instantiate the template there with double as the type. Okay, something goes wrong there. Okay, driven by the enable if. Okay, the substituting double in for t there does not create a syntactically valid function, and so the compiler just drops it on the floor as it's building its overload set. And so for the fourth call there, the overload set consists of the first function and the third function. Anybody on that side? Go ahead.
So it doesn't see it. It never enters the overload set. But does the compiler ever try to parse the templated version without a return value? So I guess it would just look like template type name t and then func t val return 1. Or it's an implementation detail that's not really relevant.
So the question was, he said, I get that it doesn't actually enter the overload set, but does the compiler actually try to parse this without those 2 lines in between? And the answer is, yeah, that's an implementation detail. What I suspect happens, but I haven't looked in a while, is that if the condition is false, okay, there's no nested typedef named type in that struct. And so what happens is it tries to generate type, gets says, no, I have no type. So marks that as a substitution failure and does not add it to the overload set. Because the template failed to, when I substitute double in there, I cannot actually generate a syntactically valid function. Yes, in the back. Yes. Yeah. Well.
I don't see how it works from that, but the syntax isn't as bad these days, really, right?
Yeah. This is if we were doing this all in C++ 14, yeah, I'd be using, instead of value and type, I'd be using the shortcuts for v and t, which I mentioned briefly earlier. We'd write this as standard is integral v t, comma int, and it would be standard enable if t underscore t instead of the colon value. And it would be noticeably shorter, but it would be C++ 14 only. And so I didn't want to do that. Okay. Any other questions? How we doing? Oh, perfect. 50. Oh, there's a question.
Somebody asked about trailing return type. I just tried it. Just out of curiosity, it works explained, so probably.
Okay. The comment was he tried the trailing return type, was putting the enable if in the trailing return type?
Yeah.
Okay. And he's tried it with Clang, and it worked. So it's probably legal.
And it's sometimes necessary if you want to check in the enable if something about the parameter.
Right. His comment was that sometimes it's necessary because if you want to check something about the parameter list in the return type, then you have to do things as a trailing return type. And that's absolutely correct. So that would imply that, yes, it is legal. And you need to be able to do it. All right. Thank you, everybody, for coming.